Well, hello again. This is Mark Summers from Summers Technical Services. We're going to do a little project here dealing with orthotropic materials and how they behave under static loads. And comparing, we'll be doing some hand calculations to calculate stresses, strains, and deflections. And then we'll also do some SOLIDWORKS simulation and some ANSYS simulations to compare those results to our hand calculations and make sure our model correlates correctly so we can have confidence that the model is going to predict our solutions for more complex geometry. So let's get started. So first off, we're going to review different material properties, and the first one we're going to talk about is isotropic materials. This is the one we start off in my 3311 Mechanics of Materials class. And what it does, it assumes that the material properties are the same in any direction. So in the X direction, you pull and push on it, Y direction, Z direction. But not only those directions, but any combination of directions, it doesn't matter. The material behaves the same way. So things like aluminum alloys, steel, stainless steels, many different types of engineering materials that we use on a regular basis are isotropic, and it makes it a lot simpler because we have fewer mechanical properties to deal with. So let's review isotropic materials. And so here is a specimen I've drawn here, and it's a tensile specimen. We're going to put in a tensile test machine. We're going to pull on the ends, and it starts off looking like the red shape. This might be a cylindrical specimen. And as we load it, as we pull on it, it's going to stretch. And so it starts off at L0 length, and as you pull on it, it's going to grow in length. As the harder you pull, the longer it's going to grow, and we'll call that L sub naught plus delta L. The change in length is how much is added to the original length as you pull on it. But you'll also notice that as you pull on it in the axial direction, it also contracts in the other two directions, the lateral directions. And that's due to something called the Poisson effect we'll talk about in a little bit. So we can do this test specimen, we can do this test, and we're going to define a couple of different properties. And the first thing we're going to define is normal stress, which is signified by sigma. And normal stress is just the axial force divided by the original cross-sectional area. So even though the area shrinks as we pull on it, we call this engineering stress. We just use the original area as we for the area, and so we take the force divided by the original area as we pull on it to get the stress. So as the force goes up, the stress goes up accordingly. And another parameter we'll define is strain, and strain is defined as the change in length divided by the original length. So that's a unitless parameter, whether you're in millimeters or inches. So those are just definitions. We define stress as force over area, and we define strain as change in length over the original length. So now let's look at this test specimen, and let's pretend like we take an infinitesimal sized element and we blow it up, and we look at it real closely, and I've blown it up into this cuboid over here on the side. And let's define our different states of stress. And so I've got my coordinate system there, and so let me turn on red here. I'm going to draw the normal stresses on this element, and we label these things based on the direction that they act. And so we're going to call this sigma x in the x direction. And since we're pulling on both ends, it's in static equilibrium, so it's just sitting there. So we've got a sigma x going this way. We've got a sigma x going this, or sigma y, normal stress in the y direction. And in the tensile specimen case, there is no force in the y direction. But we could have and we usually have a situation where we're pulling in multiple directions. So we're going to define all the different stresses that are possible, not the ones necessarily in the tensile test. And then the z direction has a normal force as well. We'll call that sigma z. sigma z. So this stress element is still in static equilibrium. Now we're going to define shear stresses. Shear stresses are stresses caused by forces not normal. That's why they call it normal stress. Normal stresses are caused by normal forces on faces. Shear stresses are caused by shear forces on faces, which means the force is parallel to the surface, to the face, as opposed to normal to. And so we have a convention we use to label these, and I'll draw these in this direction here. And so this is the x face, and so we call this tau x face y direction. Shear stress on the x face in the y direction. And then this one is tau x face in the z direction. And we have similar stresses on this face and this face. And this one here is going to be a tau z because it's on the z face and it is in the x direction. This one up here is tau z, again on the z face, and this one is in the y direction. And we can close this thing out by putting one over here and one over here in this direction. I don't think I'm paying attention too much to the directions because they should be in static equilibrium. But I think you'll get the idea. So this is tau y. This is the y face. This one's tau y. This one's in the z direction, and this one is in the x direction. So I've got 6 normal stresses. It's a general case for loads in all different directions. I'll have 3 different normal stresses and 6 different shear stresses on my stress element. Okay, so we've got that defined. Let's go look at going back to our test specimen. Let's see what we can do with this data that we've got from our test results. And the first thing I'll do is label these some of these points on this curve. So this curve right here is what we get out of our stress strain, or out of our tensile test, is a stress strain curve. And so we plot stress on the y-axis and strain on the x-axis, and we just plot the data points until the specimen breaks over here. And so let's define some additional points on this plot, our material plot. And there's a point up here, and again, this is materials that are isotropic and obey Hooke's law that we'll talk about in a minute. This point right here is the proportional limit, and that represents the point at which that portion of the curve no longer is linear. And so if I'm below the proportional limit on stress and strain, then it obeys Hooke's law. If I'm above that point, beyond that point, then it no longer obeys Hooke's law. So most of my calculations I do with my equations when I'm using isotropic materials with linear static conditions, I'm assuming I'm always below the proportional limit. All right, we've got another point we want to define here. This point right here, this is the yield point. And I'll call that YP, I guess. I'll write it out here. That's the yield point, or the yield strength. And the yield point is defined as the point at which you get increased strain with no increase in stress. So in this case, this particular data, it's got a little wiggle right there. It just kind of goes horizontal. And that represents the yield point of the material. And then the last point we'll talk about is this point right here. And this is the ultimate strength. And that's just where the stress-strain curve reaches a maximum. So these are materials that are in material handbooks that we'll use when we're calculating factors of safety and determining if our design meets code or not. So you get a lot of information out of the stress-strain curve. And maybe the last thing is this point over here. We'll get a different color here maybe. So if I take the failure point here and I drop this down to the x-axis, this strain at this point here, this is the this is another material property, and we'll call it sigma. I don't know what we'll call it, but it's another mechanical property that we use to determine if materials are ductile or brittle. And so we'll talk about that more later. All right, so let's move on to Hooke's law. And pretty sharp fella here, Mr. Hooke. This is 300 plus years ago, doing testing and testing things like aluminum and steel and other engineering materials that we use today. He found out, he discovered that a lot of these materials behave this way, where the stress and strain is proportional. So the harder you pull on it, it's a linear relationship between stress and strain. And so we call it Hooke's law. And the way you write it mathematically is you define something called E, which is we call it Young's modulus. Or sometimes we'll call it elastic modulus. And it's just defined, as per our curve up there, as stress over strain. And so the slope of this curve right here, by definition, is Young's modulus. And that's a very important property for engineering materials that obey Hooke's law. And it's a measure of the stiffness, how hard you have to pull on it to get a certain deflection. Another material property we need to keep track of is shear modulus, and we designate that with G. And shear modulus is similar to Young's modulus, but instead of normal stress over normal strain, it is shear stress divided by shear strain, which we usually write as gamma. So that's another material property. And getting back to our discussion about that lateral and longitudinal deflection, when you pull on it in the axial direction, it shrinks in the other direction. We've got this picture at the bottom down here that does a good job explaining what Young's modulus is. And so you can see that we start off with the green box, and as you pull on it, it stretches in the axial direction, but it also contracts in the lateral direction, both lateral directions. And so we define this property called the Poisson ratio. And I'll write that equation up here. I'll scoot this thing over here. Running out of room. And so the Poisson ratio is minus the lateral strain divided by the axial strain. So that's a ratio of how much the strain is along the direction you're actually pulling it, or excuse me, the other way around. The ratio between the strain in the lateral direction divided by the strain in the axial direction. And for most materials, this is, maybe about 0.3 for most isotropic materials that we'll deal with. All right, so these material properties, again, we're going to be using these extensively when we do our stress calculations and deflection calculations. These are all very important parameters. And so this is hopefully just a review from 3311. All right, let's move into orthotropic materials. And so orthotropic materials are materials that, isotropic, I guess I should have explained the definition. Iso means same, and tropic, I think, means direction. So it's got the same material properties in any direction. Orthotropic means that it's not isotropic. What it means is that it has potentially different material properties in 3 different directions. So if you define an x direction, a y direction, and a z direction, it potentially has different Young's modulus and shear modulus and Poisson ratios in each of those 3 directions. And so that's the definition of an orthotropic material. So if we take our Hooke's law equations and use them on our stress element that we drew last time, we have all the different, even though we don't have all of the forces in all the directions on our load tests, in general we could have loads in all directions. And so we've got all of our different stress elements. If you write that down in matrix form, you can get these matrices here. So the compliance matrix is the first one we'll talk about. Compliance matrix sets the strains over here, and if you the nomenclature is slightly different than what I'm used to. The first three epsilons, those are strains, those are axial strains. And these, I would have labeled these, if I would have made this chart, I would have labeled those gammas. Those are the shear strains in the other three, all three faces. So they label them all as epsilons. I would have labeled the last three as gammas to keep them separate. And the same thing over here on the strain, or the stress values, sigma, x, x, y, y, z, z, those make sense. Those are the strain on the x face in the x direction, stress and s. So the first three are normal stresses, and these last three I would have called, I would have put taus in front of them. Those are shear stresses, but they call them sigmas. So, but they've got the right suffix, or the right nomenclature: y, z, z, x, x, y. All right, and then in the middle here, the matrix is turning our equations into matrix form, and you can see we've got our familiar parameters. So there's Young's modulus in the x direction, there's Young's modulus in the y and z directions, and I've also got shear modulus in 3 directions, and then the rest of these are there's the Poisson ratios up here. And so that's just matrix form of the compliance matrix for a general orthotropic material. And then if you do some matrix algebra and come up with an inverse matrix of the compliance matrix, so you multiply 2 matrices together, you get the identity matrix, you can get this other version of it, which is called the stiffness matrix, and this is what I'm used to seeing when we're dealing with finite element analysis calculations. Generally, you talk about the stiffness matrix, and that's the matrix that the finite element analysis program creates to calculate the strains, displacements, and then the strains, and then eventually the stresses. And so you get the same parameters involved with it. So it turns out that for orthotropic materials that we talked about, I haven't talked about it yet. So here's the different material properties that you have for general orthotropic materials. So we've got 3 values for Young's modulus. We got 3 values for shear modulus, and we've got 6 values for Poisson's ratio. But it turns out that some of these are related, and let's identify the ones that are related. So it turns out that the Poisson ratio xy is equal to Poisson ratio yx, and so those are really just one parameter. And same thing with Poisson ratio zx and xz, I think I got those right. And then one more pair down here, these are equal. So instead of having 12 independent, unique material properties, it turns out there's really only 9 that you have to define to compute all the displacements and eventually all the strains and stresses because of some of these symmetries. And so we'll be dealing with 9 different material properties when we do our SOLIDWORKS simulation or our hand calculations, either one, to be able to calculate these strains and stresses. All right, so let's go back to the isotropic material to kind of close the loop on that. We talked initially that there was 3 different parameters. There's a Young's modulus, a shear modulus, and a Poisson ratio. But it turns out for similar reasons, there's only really 2 independent material properties on isotropic materials because of this relationship that I can write down here, if I can remember it. So Young's modulus you can write as 2 times 1 plus the Poisson ratio times the shear modulus. And so that equation relates all 3 parameters together, which means that if you have any 2, you can always calculate the 3rd one. So we say there's two independent material properties for isotropic materials. Okay, so I think that gets us through definition and explaining some of these properties of orthotropic materials. So our last sheet here, we get to finally talk about what we come here for is for this SolidWorks simulation. So we'll first part we'll be doing simulation in SolidWorks, and then we'll follow that up with another simulation using ANSYS, and we can compare those results and see how they compare to our hand calculations. So what we're going to do is, if I can find it here, yeah, here it is. So we're going to do an analysis on this test specimen, and this is created down in Dr. Tate's lab downstairs, and it is made out of some material that my friend Dr. Harish Kalagunta, I hope I pronounced that right. He's a recent graduate of the MSEC program out here at Texas State, and he's done a lot of research on studying these kind of materials. Anyway, they made this. This is a test specimen we use in mechanics and materials class. So we're going to use this, and it was created. It's a standardized test so that you can test these materials anywhere you want to be, as long as you follow that standard. So it's an ASTM D7078 standard that defines the entire testing processes, and I guess the title of it is Shear Properties of Composite. So it explains how to calculate and quantify and do testing to compute shear properties for laminate composites. And so this particular test specimen has got 6 layers, and you can see the dimensions. This sketch here is right out of D7078 specification. And the pictures at the bottom are some schematics of what this laminate looks like. So there's 6 layers of this thing with an epoxy binder. And what they do is each layer has its own weave that looks like the picture at the bottom. It's got a weave that goes in the X direction and a weave that goes in the Y direction that interlaces with the two. And so it turns out that for this particular test, this Young's modulus in the X direction and Young's modulus in the Y direction, Young's modulus in the Z direction, we're going to input all 3 of those parameters, but 2 of them are going to be equal. Young's modulus in the X and Young's modulus in the Y is the same because it looks the same whether I rotate it 90 degrees or not. Now in the Z direction, it's going to be a lot weaker because you're pulling across those plies and you're not getting that strength of that reinforcement material. So 2 of the 3 Young's modulus values will be identical. We'll still, in the Z direction will be less, and we'll input all those values, all 9 values that we talked about before, into the material properties. But pairs of them are going to be equal. Same thing with shear modulus, and same thing with Poisson ratio. There'll be 2 of the 3 of each of those 3 sets will be identical. And the other picture is pretty interesting. It's actually each one of those individual woven paths on the bottom left picture there is actually made up of several fibers, and so it's a very efficient material, and that woven type material is evidently very advantageous, and that's part of Dr. Kalagunta's research has been. So anyway, that takes us through the little preliminary discussions, getting us up to speed on the material properties. Now what I want you to do is go get a copy of that spec. We have access to ASTM specifications through ASTM Compass that the university pays a lot of money for, so take advantage of it. Log on, go to ASTM Compass, download that spec, get the sketch, and find out more information about how the tests are done. And I want you to make a SolidWorks model of this test specimen, just a single feature. Just do a sketch and extrude per the dimensions there in the specification and on the screen there. And make sure you get it in the right orientation. It's got an X and a Y and Z direction. Build a model in that direction so that when we apply these material properties, we're going to be assigned as X, Y, and Z direction. And if you have that model built in the wrong orientation, your material is not going to be applied correctly. You're going to get the wrong answer. So anyway, I hope that was helpful to get us back up to speed on material properties, and watch for the next video coming up where we do our actual SolidWorks simulation. I'll walk you through the steps of defining the material, and we have to also define the laminate, the number of layers and that kind of thing. And so I'll show you how to do all that, and then we'll get some numbers, and then we'll move on and do the same thing in ANSYS later on. So that's all I've got for now. Enjoy the day, and we'll see you next time. Again, this is Mark Summers from Summers Technical Services.